What's up, guys? It's me, Sir Ernest, and today we're going to talk about the angular momentum of rigid objects and its relationship to the torque exerted on it. So consider we have a rigid object wherein it contains a lot of particles. This particle represents all those particles, and this is defined by its mass mi, its position vector Ri, as well as its translational velocity Vi, which is due to the rotation along the xy axis towards the counterclockwise direction. So if this is your angular speed, therefore the angular velocity will be along the z direction. Okay, here we assume that this object is rotating about your z-axis. So, for a particle I, the angular momentum is given by Li vector, and this is equal to the cross product of its position vector and the translational momentum or your linear momentum Pi. And this is defined as the product of the mass of that particle, mi, and the velocity vi. So by definition of your cross product, because remember that the position vector is always perpendicular to your velocity vector, so therefore the angle between them is always 90 degrees. So therefore the magnitude of your angular momentum Li would be equal to the product of mi vi times Ri. And by definition again, omega is equal to vi over Ri. So therefore, this is now equal to mi Ri squared omega. Since the direction is z-axis, therefore Li, which is equal to Li magnitude k hat, so this is equal to mi Ri squared omega k hat. So we already defined that omega vector is omega k hat. So therefore, this is equal to mi Ri squared omega vector. So the total angular momentum of the system, L. So here we put in the subscript z to indicate that the angular momentum is due to its rotation about the z-axis. And this is just the sum of the individual angular momentum of each of the particle within the system. So this is equal to sum of mi Ri squared for all I times omega. And we know that this is defined to be the angular momentum of this rigid object about the z-axis. So therefore, we can finally rewrite this as Iz omega vector. So this is now your angular momentum of this rigid object about the z-axis. Now we already know that the total torque exerted on objects, for example, is actually the rate of change of your angular momentum with respect to time. And this is for any system that rotates about our z-axis. And again, by definition, this is now equal to the total derivative with respect to time of this expression. So this is Iz omega. And we already know that the moment of inertia of a rigid object rotating about a fixed axis is constant. So therefore, this is equal to Iz times the derivative of omega with respect to time, or simply Iz omega dot. So these are now your expressions for the total angular momentum of your rigid object rotating about a fixed axis and the torque exerted on your object about the fixed axis. And in the next video, we're going to summarize this and have it related to the equations we use for momentum, for force, and kinetic energy for both translation and rotation about the fixed axis. And we will see the similarities of our expressions. But for now, thank you guys for watching. I hope you learned something today. And I'll see you guys in the next video. Bye-bye.